If you step outside on a calm afternoon, close your eyes, and stand perfectly still, the world feels completely motionless. But if you happen to be standing near the equator, the ground beneath your feet is hurtling eastward at roughly 1,000 miles per hour. For thousands of years, humans trusted this physical feedback. We looked out at the horizon, felt no wind or vibration, and rationally concluded that we lived on a flat, stationary plane with the cosmos revolving around us. To actually understand the mechanics of the planet we live on, we first have to recognize that our physical senses are actively deceiving us. The reason we fail to feel this violent speed comes down to Isaac Newton's laws of motion. Specifically, the law of inertia. Human biology is incapable of feeling constant velocity. We only feel acceleration, which is a change in speed or a change in direction. We exist inside a closed system. The ground, the trees, the buildings, and the atmosphere around you have been traveling at the exact same constant speed since the day you were born. Because you and your immediate environment share that matching speed, your relative acceleration is zero. According to physics, if there is no acceleration, the net force pushing against you is zero. However, rotation is a massive circular path. Traveling in a circle requires you to constantly change direction, which mathematically counts as acceleration. If we are constantly curving, why aren't we thrown outward off the surface? That outward throw is countered by an incredibly powerful center-seeking force, gravity. Gravity continuously pulls your mass toward the core, vastly overpowering that slight outward rotational acceleration and effectively pinning you to the curve. Together, inertia and gravity build a flawless censoring void, completely masking the reality that we are spinning fast enough to outpace a commercial jet. If our biology prevents us from feeling this motion, how can we build a machine to prove it is actually happening? In 1851, French physicist Léon Foucault bypassed human perception entirely by installing a massive experimental apparatus inside the Pantheon in Paris. He suspended a heavy brass weight from a long wire high up in the dome. Once set in motion, a pendulum swinging freely from that extreme height effectively isolates itself from the surrounding rotational frame of the Earth. This image displays the numbered dial positioned directly beneath the bob. If you watch the swings over several hours, the path appears to slowly rotate across these numbers. But the pendulum's plane of oscillation isn't turning, the Earth is simply turning beneath it. Foucault's heavy brass weight provides undeniable visual proof that our localized feeling of stillness is a biological blind spot. While we can use a pendulum to glimpse the spin in one room, the true scale of this invisible engine becomes clear when we look at the macro systems covering our planet. Long ago, a massive collision knocked the young Earth off kilter. Today, our rotation happens on a tilted axis, exposing different hemispheres to direct sunlight throughout the year, and physically driving the cycle of our seasons. Because the planet is a sphere, the equator rotates much faster than the poles. As air and water travel across these different latitudes, their paths deflect, creating what we call the Coriolis effect. This map illustrates the result. The Coriolis effect directly dictates the flow of the world's winds, which in turn physically drive the oceans into the massive circulating gyres shown by these blue arrows. The rotational force we fail to feel every day acts as the primary engine sculpting global weather patterns, ocean temperatures, and the overall habitability of the globe. Yet there is a critical flaw built into this massive planetary engine. The spin is not perfectly constant. The gravitational pull of the moon creates tidal friction, and internal physical shifts within the core act together as a planetary brake, causing the Earth's rotation to gradually slow down over time. This chart plots astronomical records since the 1600s, tracking the length of a day. It reveals a measurable deceleration of our rotation. Despite short-term fluctuations, that diagonal line tracks the long-term trend, showing a single day lengthens by roughly 1.4 milliseconds every century. That fraction of a millisecond creates severe complications for modern technology. Advanced satellite systems like GPS require pinpoint atomic accuracy and must continuously track this decaying physical rotation to function correctly. To prevent navigation systems from failing, scientists closely monitor a standard called UT1 and periodically inject leap seconds into our atomic clocks to force our digital time back into sync with physical reality. So while you may feel perfectly still right now, every aspect of human life, from the arrival of winter to the ocean breeze to the map guiding your phone, relies entirely on the silent, degrading spin of the world beneath your feet.